Hello everyone, welcome to my videos on elementary differential equations. This is video number 10 for chapter 3. In this video, we will take several examples for the case where the characteristic equation has repeated roots. Okay, let's get started. So the first example, example number 2, is the following. We want to solve the initial value problem, y double prime plus 2y prime plus y equals 0, where the initial values are given y0 is 2, y prime as 0 is 1. So by now we shall be quite familiar with the procedure, maybe even automatic. We will set up the characteristic equation and find out that it has two roots, -1, and then immediately we can set up the general solution, that is e to the negative t, which is the r, and then multiply by c1 plus c2t. So here the c1 and c2 are the two constants that you will determine using the initial values. Okay, so let's put in the initial values and see what we get. y0 equal 2, so put t to be 0, this gives me 1, and this is 0, so I get c1. And then c1 must be 2, so immediately we have that. And then to find c2, we need to use the second condition, y prime as 0 equal 1. So let's differentiate the solution and write out its derivative. And this is just the product rule. Okay, we see that if we differentiate et, we get a negative sign outside the bracket. And then we can differentiate this polynomial and we get c2. And now setting t to be 0, we get here it will be just negative c1. And then here we get a c2 equals 1. And now we can compute c2. c2 will be just 1 plus c1 using the c1 value, which is 2 we have found. So c2 is 3. Okay, now we can put these two numbers back in and easily write out the solution. That is 2 plus 3t in bracket times e to the negative t. Okay, so let's ask one more question here. So how would the graph of y look like? What about the asymptotic behavior? Does y go to 0 as t goes to infinity? Okay, so I leave this question to the readers and to the viewers that try to figure out. And the hint will be an example we had in the previous video. If you forgot, you can take a look and that'll help you answer this question. Okay, so let's take a variation of this example. It's the same example, but we change the initial condition into y at 2 is 2 and y prime at 2 is 1. Okay, so such initial values that are given not at 0 but at another value for t naught we have seen before. And from that example we learned that when we wrote the general solution, it's more convenient for the future computation to write it in the following way. That is, wherever you have t, I will put t minus 2. So yt will be c1 times e to the negative t minus 2, and then c2, and this becomes t minus 2 and e to the negative t minus 2. Okay, and this you will see soon that will make the next step easier. Okay, so before we put in the initial values, let's write out y prime because it's needed. We'll have that. So we differentiate this with respect to t, and we get that. So this gives me a negative c in the front, and then the product rule, and this gives me c2 times that, and this term will be this term times the derivative of that, which gives me a negative term. Okay? Okay, and now let's put in the initial condition. y2, what will y2 be? Well, now you see, if you put t equals 2, then t minus 2 is 0. This is 1, and this term is 0. You get c1, which is 2. So immediately you have c1. And then what about y prime evaluated at 2? Well, we see that this is 0, so that's 1. And then that's 1, so we get negative c1 plus c2, and that's 0. So we simply get that. And then we can use this equation to quickly find out the c2 value using that c1 is 2, and we see that c2 is 3. So we have those two constants. Okay, plugging everything back in, we can write out the solution. Okay, c1 now is 2, c2 times t minus 2, e to the power negative t minus 2. Well, as a remark, I wanted to say that, of course, you can write the same general solution as in the first version of the example 2 and work out the detail. You can try that and pause the video and work that out, and you will see that in the end you get the same function, probably appear in a different way. This might be distributed and collected terms. Try that, and you will find out for yourself that if you're convinced that the other way is taking much more work. Okay, so this is another spin on the version B. Let's look at even another way of solving this equation with the initial condition given at a different time other than 0. So we see that the equation is autonomous. What does it mean is that the time variable t does not appear in the equation. Okay, so if that is the case, then you can do the following manipulation. So let now the initial data be given at t0 equals 2. Then we can introduce a new time variable. We simply shift it. We call it tau, which is t minus t0. Here will be t minus 2. We just shift the time by 2 units. Okay. And now we consider tau as our independent variable, and we see that d tau equals dt. So the initial value problem in the variable tau becomes y double prime in tau plus 2y prime in tau plus y tau is 0, and then y at 0 is 2, y prime at 0 is 1, which is the same as the example 2. Okay, then you can go about and solve it in the standard way, and then you'll find the solution. And then remember to write tau in the solution instead of t. And then once you have that, if you want to recover the function y as a function of t, then you can put back in tau equals t minus 2 in this solution, and we'll get 2 plus 3 t minus 2 and e to the power negative t minus 2. And of course, there's no surprise that this is exactly the same as we get in example 2b. Okay, so now we have covered all 3 different types of roots for the characteristic equation, and that is all you need to determine the general solution. So let's do a summary. For the homogeneous constant coefficient second order differential equation in this form, ay double prime plus by plus cy equals 0, and then this is the characteristic equation, a polynomial of degree 2 in R, ar squared plus br plus c equals 0. And then let the 2 roots be R1 and R2. Okay, and then we have the following. First case, R1 and R2 are real and distinct. Then the general solution is the summation of 2 exponential functions, a linear combination of that, with R1 and R2 as the rate. Second case is that R1 and R2 are real and are the same. R1 equals R2. And call it the number R bar here. And then your general solution is the exponential function multiplied by C1 plus C2t. Finally, if we have complex roots, then the two complex roots are complex conjugate, and we can write it into the real part plus minus I times the imaginary part. And let the lambda be the real part and mu be the imaginary part. Then the general solution is the following. It is a product of two parts. One is e to the lambda t, an exponential function with the real part as the rate. This is multiplied with a sum of the sine cosine with mu in front of t and a linear combination of them. So C1 times cosine plus C2 times sine of mu t. Okay, so I hope that this summary gives you a complete picture of general solutions for second order differential equation with constant coefficient and homogeneous, meaning 0 on the right hand side. So this covers all cases. Okay, so that's all I have to say for this video. I hope you enjoyed it, and I look forward to seeing you next time.